Hi everyone, my name is Muhammet Talha Uyar. I am a senior student at Bilkent University and this is my term project for the EEE 474 Foundations of Magnetic Resonance Imaging class. My project topic is visualizing the effects of changes in decay space to an image. To give a little bit of background information, my project is mainly inspired by the problem 5.7 from our course textbook, Principles of Magnetic Resonance Imaging by Dwight Nishimura. In the question, an original image was given and some changes in the decay space domain were applied. As a result of these changes, the new image output was asked. The aim of my project is to simply generalize and visualize this question in MATLAB environment. To reach my goal, a simple procedure is followed. First, we take an input image as the original image. Then, we use the 2D Fourier transform function to go to decay space domain. We also use the FFT shift function shift so that the central frequency component of the image is at the origin. After we find a matrix denoting the data in decay space for the original image, we simply fill another decay space matrix according to the changes that are made. Finally, we take the inverse 2D Fourier transform to find the modulated image. In the project, the effects of following changes are visualized. Firstly, the effect of changing the magnitude of the gradient pulses are investigated. Then, changing the sampling rate of phasing codes is depicted. Finally, the effects of applying 90-degree X and Y pulses are examined. Let's start with changing the magnitude of the gradient pulses. When the magnitude of the gradient pulses change, the area under the gradient pulse changes according to the following ratios. This area change will affect the result of the integration with the same ratio. Hence, this will simply change the range of Kx and Ky, thus changing the maximum values as well. To visualize this effect, we can simply copy the values from the original decay space when they are in the new range and fill with 0 for the values that are no longer in the range. Here, we can see the results that are acquired by the visualization. On the top left, we can see the original image and the modified images when the Kx and Ky ranges are changed according to the ratio values. As you can clearly see, the resolution is affected by this change. This was expected considering that the decay space domain is simply the 2D Fourier transform of the image. By changing the range of Kx and Ky, we are no longer including the high-frequency components in Fourier domain, and by not including the high-frequency components, we are reducing the resolution of the image. Secondly, let's examine the effects of changing the sampling rate of the phasing codes. Now, since we are dealing with a discrete data point, i.e. we are not dealing with a real-life object and only dealing with an image of the object, the visualization of changing the sampling rate will not be 100% accurate. Instead of changing the sampling rate of a continuous data, we will upsample and downsample a discrete dataset. Changing the sampling rate will change the field of view, and we will zoom in and zoom out the image accordingly. This will sometimes cause aliasing, as we will see in the next slide. To prevent aliasing, we can apply a simple filter to select a portion of the image and apply these changes later on. As we can see by upsampling, we are decreasing the distance between the sample points in the decay space. This increases the field of view, hence we zoom out. Since the inverse Fourier transform generates infinitely many copies of the image, by zooming out, we are seeing the other copies of the image on the right and left hand side of the original image. Here, we can also see the effects of downsampling. When we downsample, the distance between the sample points in the decay space increases. This decreases the field of view and we, as a result, see a zoomed-in version of the image. We focus on an overlap of different copies of the original image. This is called aliasing. To prevent this, we simply apply a filter depicted in bottom left and then apply the downsampling. As a result, we can see that we still focus on 4 different images, but now they do not overlap. Finally, we will visualize the effects of applying 90-degree X and Y pulses through the phasing codes. This is easy to simulate because these pulses simply modulate the phasing code data by 1, -1, I, and -I respectively. After multiplying the decay space data accordingly, we can find the output images by taking the inverse Fourier transform. As we can see, applying 90-degree X and -90-degree X pulse through the phasing codes is equivalent to convolving the original image with 2 impulses at the top and bottom of the image. The effect of applying 90-degree X, 90-degree Y, -90-degree X and -90-degree Y pulses are also depicted in the slide. Thank you for listening to my project presentation.